hitting start now.
Good morning to those tuning in to today's webcast presentation of Evaluating EOR and Flood Performance, Optimizing Well Pad Development. It's my pleasure to introduce today's presenter, Patrick Hayes, the North America Business Development Manager at Tracerco. With over 15 years of experience at Tracerco, Patrick has established his expertise in chemical tracer technology by managing projects across the globe, improving efficiencies and capital investment for upstream, midstream, and downstream business units. Now, for those unfamiliar with Tracerco, it's a world-leading industrial technology company that has developed and used tracer diagnostic and measurement tools in a number of different industries. Behind the scenes, it has improved safety, security, and technical understanding through activities as varied as fuel security programs, cutting-edge radiation monitors, and of course, oilfield operations. Its reservoir group has over 40 years of experience helping oil companies understand the movement of fluids within their reservoirs and help them make informed decisions that affect their drilling, completion, and production strategy. In today's talk, Patrick will cover how different tracer types are applied and interpreted, and explain how the knowledge and understanding gained from a tracer study can affect the financial bottom line. Afterwards, he and Tracerco's Global Marketing Manager, Paul Hewitt, will answer live questions you might have about the presentation or tracer technology in general. With that, Patrick, let's begin.
Thanks for the introduction, Sadipcha. As promised, today's presentation will cover a range of applications with some in-depth dives into tracer technologies. I'm excited to present the case studies as they are novel examples of how tracer technology can be applied, provide quick return on investment. We'll be starting with an overview of the fundamentals of technology and items that many projects have in common. We will discuss controlled release tracer projects, incorporating the tracers used, project design considerations, and more. EOR projects will include injected gas and water applications, as well as ASP flood example. In this section, we will cover the project design and data interpretation. Finally, we will wrap things up with a look at unconventional applications, how these measurements work, and how they will help finding the best rock, well spacing, and completions design. The presentation will discuss how to be successful at generating the return on investment, project design, and some items to be taken into consideration. Once the presentation is completed, we will have some time for questions and answers. I would like to encourage those with questions to use the Q&A tab on the upper right side of your screen. As Sadipja mentioned, Paul will be looking at these during the presentation. Please relax and enjoy the presentation. When thinking about tracer technology, there are several common applications, but using the right tracers for the right application is critical to getting the return on investment. The misuse and misunderstanding of tracer properties has provided a lot of room for failed projects, incomplete data, and misunderstanding. Chemical tracer applications can be typically grouped into three primary categories. Controlled release tracers are attached to the jewelry downhole for zonal contribution for years or lifetime of the well. The lifespan of tracers' responses are dependent on the mass that can be applied and flow rates of the intended phase. Second are liquid tracers applied during injection to understand the relationships and communication to the producer for enhanced oil recovery. These tracers can provide valuable data on the connection between the wells, such as insight to the effectiveness of injection programs. They are highly specialized and can even be designed to provide residual oil measurements. Third technology we look at today covers the wide range of stimulations and unconventional applications for different data sets. These data sets include several unique quantification measurements of the water, oil, and gas phases. All of these applications provide unique data sets that can help characterize the reservoir, enhance production, and lower operating costs that affect the CapEx and OpEx spend. When using tracers, there are some major fundamental items that need to be considered. The environment that tracers encounter needs not affect the tracer's signature or behavior. If there are interactions with the reservoir environment, there will be an impact on the results. Stability is key to success. For almost any tracer project, setting clear objectives is going to be key to success in getting that return on investment. This seems simple, like simple and upfront items. It's not. Project objectives need to be clear, understanding what needs to be measured. Don't overcomplicate the objectives and don't make too many changes at once. That can complicate things and impact results. Remember the scientific method. Understand what are the types of tracers are needed and what volumes will be involved with the project. Plan to operate on a worst case. The volumes and the phases can affect the longevity of the project and can hinder the objectives. What is the minimum we need to measure and for how long? The impact on logistics are usually minimal. However, frequent early sampling in the project can be strenuous on resources. Dealing with H2S, processing systems, and working environments can pose challenges for operations. Working as a team and having the operations organized ahead of time can reduce project risks and reduce project costs. We start the review of projects and types of applications with a look into controlled release tracer technologies, tracer design, data acquisition, analysis, and case studies. If you have or have not had exposure to solid tracers, here are a few bits of information that may be important to know. If you have or have not had exposure to solid tracers, here are a few bits of information that are important to know. 1, solid tracer bars do not erode. The tracer is diffused out of the polymer, providing linear release. 2, high concentrations of tracer from the solid does not mean a high flow rate. The reverse is true. A higher flow rate dilutes the release of tracer to a greater degree. 3, polymer enclosed tracers are quantifiable through the lifetime of the well. This is particularly true. Tracers require a period of shut-in to build a localized tracer cloud. The shape and speed of the surface of the cloud allows flow to be quantified. This can be measured at any time in the life of the well, so long as tracers remain. Controlled release tracers have some specific design considerations. I've listed a few main points. Projects design should always look at the health, safety, and environment from the installment stage to the sample collection. This includes logistics and operations. The flow rate of the phase produced and artificial lift used will affect concentrations. Reservoir temperature and fluid types impact longevity. Commingled flow and downstream dilution further reduces the limits of quantification. Transient study timing, planning, and logistics needs to be considered ahead of time. We'll talk a bit about the analysis and what we can learn. We start with the relative and quantitative information. The far left presents if a zone is flowing or not, while the second from the left presents the known location of tracers on the horizontal. Tracers are phase specific. If water and oil tracers are in the same location and the release rate is understood, we can calculate the water cut or when water ingress begins. We can look at the integrity and tool function like the example of holding and passing seals. In addition, we can detect leaks or open valves. Finally, on the right, by using a transient study, the quantity of flow per zone can be resolved. This uses the pulse and decay curve analysis. I mentioned the use of a transient study in order to capitalize on the opportunity to quantify zonal production. In order to do this, the production pipe length, tracer locations, dimensions, and expected produced volumes need to be known. Volumes and the production system design can affect the tracer pulse's arrival timing at the sample location, requiring changes to the schedules. Sampling must be done during the correct timing to capture the breakthrough, peak, and mode. Based on the arrival timing, volume produced, and volumes between the where the tracers are located, we can quantify the production along the lateral. This slide presents what actual tracer curves may look like. After being shut in, the tracer clouds are produced as pulses, located on the left, and the decay curves are used to calculate the volumes, located on the right, not the concentrations directly. Looking at the pulses, we can characterize the flow as strong towards the heel, indicated by the steep pulses. Weaker moving towards the toe as the tail becomes elongated, and toe production was not present. Pulse velocity testing uses the timing of arrival as indicated on the right line graphs, while the decay curve method analyzes the tail and can help calculate the volumes as presented on the right. In some cases, crossflow can also be diagnosed utilizing this technique. We've gone through several topics leading to the project's successes, and now we will move to reviewing case study. The case study reviews the comparison of using tracers to a conventional production log. We discuss the transient analysis, steady state results, and do a comparison. We start on the left looking at the project planning with 5 formation zones identified that are subject to the investigation. These formations are named starting from the shallowest, A1, A3, A5, A7, and A9. Just to be a little confusing, the tracer numbers are starting from the toe and formation numbers from the shallowest zone to the deepest zone. Due to a larger number of tracers available than zones produced, several zones were broken into multiple sections. This created more definition along the wellbore and more comprehensive information to compare to log data. Based on the expected volumes and the wellbore design, the sampling timing was forecasted to ensure the transient tested would be successful. The tracer masses were calculated to meet project timing goals and then applied to the base pipe and covered with screens. The top bar graph provides the oil production per zone and the zones broken into subsections, such as A5, where 3 oil tracers were used. The toe of the well starts on the far right with A9, traced with oil tracer 1 and oil tracer 2. The cumulative production or total for the zones are combined at the top of zones A5 and zones A7. These 2 zones combined produce nearly 75% of the total production of the well. The line graph to the upper right presents the detailed transient analysis. Below, the blue presents the water influx. A7 was traced in 2 sections. The third bar from the right has produced nearly 55% of the water, and the water tracer located at the upper section of A9 near the toe produced 20% of the water influx. This does not correlate to the areas with highest oil production. Water production does not mean oil recovery. When looking at data, we are often asked how it compares to PLT results. There are differences in the data and usually the timing of collection. The location monitored and the tool's abilities vary one from the other. The slide presents the data interpretation from the transient study on the top for the oil production by trace location and zone contribution, as well as the bottom, the memory PLT data. The timing of the two measurements varied slightly and were completed consecutively. The memory PLT only provided cumulative production per zone, with the exception of A5, which had 2 sections for the PLT and 3 traced zones, 3 trace sections. The boxes outline the total for the zones and the breakdown of production per location measured by both data sets. Both the PLT and the transient study showed nearly equal production for A5 and A7. However, there was a discrepancy in the production from A1 and A3. The transient study and steady state analysis showed short-term production from the 2 zones, A1 and A3, that declined in contribution following startup. This transition in production became crucial to the conclusions of the project. This reallocation of production from A1 and A3 to the tow stages makes for nearly identical match to the memory PLT. Tying the flow rates from the transient production log to the geology, reservoir characteristics, and observations of decline of zones A1 and A3's production indicated in the steady state analysis allowed for completions changes to cope with the different reservoir properties, further enhancing production for this well and subsequent wells. The use of tracers reduced logistics and project risks in comparison to the PLT, allowed for time-lapse production profiling, and required no interference or deferred production. This information alone provided significant savings, changed the wells that were completed, and impacted future planning. I want to provide the SPE number and thank those who worked on its publication. We are on to the EOR next, and two studies that utilize interwell applications. Interwell is a great way to find quick gains in the return on investment, as every barrel or scuff of gas injected has a value and estimated incremental recovery. The first case represents a field tracer study evaluating the effectiveness of water and CO2 injection, followed by a remaining oil saturation application to evaluate the efficiency of an ASP pilot. Due to the time remaining, we'll spend little time on design and planning, with a primary focus on findings of the case studies and how they were determined. Interwell project planning has some important factors that need to be taken into consideration. The primary is the amount of dilution that the tracers will encounter. The deployment is typically simple and done as a pulse, but compatibility with the injected fluid needs to be looked at. Injection rates, reservoir temperatures, as well as production dilution can affect the concentrations and changing tracer amounts needed. The project timeline can also be evaluated for possible cost savings. To ensure the project is constructed correctly, we look at 3 phases of design. The pre-deployment phase will ensure the correct tracer is chosen, the quantity is sufficient, and the sampling strategy will be effective. In the injection phase will focus on the deployment, timing needed, flush intervals if required, and operations changes needed between injection. Phase 3 is post-deployment. The sampling schedules can be adjusted to reduce cost as information begins to be reported and supports making changes to reduce those costs. The sample analysis and reporting will do the heavy lifting in delivering the results and be tailored to the objectives. Models can be updated based on the results, and adjustments can be made to gain efficiency. The amount of tracer required will be based on the information properties as described in the slide. The distance from the injector to the producer, the estimated angle of the sweep, and the levels of uncertainty. Then we must look at additional dilution that may take place, split injection, and commingled production. Further dilution from commingled injection or commingled production can cause the tracer volumes to be multiplied. In some cases, this can be significant. Luckily, with tracer analysis limits down to parts per trillion, the impacts are not as drastic as in the past. Commingled production can also cause significant dilution, having a similar impact on the tracer volumes as commingled injection. However, these operations also provide some efficiencies, such as analyzing one sample from multiple wells while looking for the first breakthrough. At the top, we start with the sampling schedules. Sampling needs collection at the correct timing, as going back in time to collect samples is not an option. We can always skip samples in the analysis to save on costs if the data suggests that this is appropriate. Usually the start of sampling is more frequent to ensure that the possible short-term breakthroughs are not missed and to capture any short rise and fall in concentrations. This can provide early critical information. Later in timing, the sampling can be further apart as more dilution has taken place and the peaks will be much wider. The parts of analysis critical for reservoir characterization and providing quantified measurements are listed below with the arrows identifying each use, each providing a part to the needed calculations to determine mass recovery, distribution, tortuosity, swept pore volume, and more. Several qualitative items can be determined using chemical tracers. Some on the short list are connectivity, breakthrough times, delineated streamlines, and fault blocks, for example. However, the mass recoveries over time, combined with different calculations, can bring more in-depth quantitative solutions to the effect of enhanced oil recovery to enhance the efficiency of enhanced oil recovery systems. The swept pore volumes, reservoir heterogeneity, and flood effectiveness can be analyzed further. Once the decline has stabilized, the tail can be extrapolated as seen in the top right. This has a positive impact on cost. It reduces the number of samples needed for analysis into the future, shortens the project timelines, and delivers earlier results. These detailed results can provide Lorentz coefficients, Dijkstra-Parsons coefficients, Shook analysis can be performed, and more. So we have a foundation built. Now let's talk case studies. The first case study being presented is focused on the use of CO2 injection and water injection across the entire field of injectors and producers, with some specific goals and objectives. The operator involved had some specific goals in mind. The goals were to gain a better understanding of the fault systems mapped in their models, mapping the networks of natural fractures, and to verify the perceived efficiencies against reality. The combination of goals and objectives would deliver the return on investment. The project layout is presented on the map. The water injectors presented as blue triangles, the gas injectors as red triangles, and the producers are identified as circles. The water injectors are utilized to create a water curtain to the east of the field, while re-injection gas and CO2 combined are the enhanced oil recovery. The water injectors and the gas injection wells were all traced with unique chemical tracers that were phase specific, so that individual injection well communication paths and contribution could be identified. Post-tracer injection, the producers were monitored and sampled. The phases sampled at each of the producers was dependent on the location of the producer and the surrounding injectors. The red and blue circles around the green producer indicates the phases sampled and those analyzed. There are many options when building a sampling program and many customized ways to save on total project cost. As seen on the map, many of the Western producers were not sampled for water tracers as a cost savings to the project. Multiple pathways of communication were identified, with some injectors presenting breakthrough at the producer in a matter of hours following injection, and other producers seeing communication taking place over multiple weeks. From a qualitative sense, looking at the communication across the entire field can appear to be a bit overwhelming. Once the individual injectors and producers' communication is established, the tracer data is looked at closer to peel back the layers, and the process of revealing true return on investment begins. Though this project provided many different findings, we will present two of the most significant findings that impacted production. We begin with the evaluation of the water curtain to the northeast section of the field. There was an expectation of some communication between the water injectors providing the curtain and the associated producers. The tracer study responses indicated two of the producers were strongly impacted by one of the injectors. These are indicated by the large blue arrows on the map and the bar chart. The concentrations of tracers over time from the traced well are presented in the line graph next to the map and plotted for the two producers. The mass recovery indicated that more than 25% of the injection water was circulating and not creating the desired curtain effect. As a result, the water injector was shut in. The associated producers had a significant increase in production of oil and gas, while the water production from the producers were halved. The western flank of the field had several outer gas injection wells. The wells were intended to help with increasing oil production to the nearby producers located in the interior of the field development. Minimal interactions were indicated by the tracer study between the gas injection wells and the producers. This was a loss of efficiency, and the injection wells were switched to water injection instead. The additional available gas created by this change was re-injected in the field, ultimately providing a greater return on investment and an uplift in the incremental recovery. As quoted from the operator, the tracer study allowed us to optimize our flood and has paid for itself many times over. This case study will be a quick intro and review of the use of partitioning tracers for remaining oil saturation and residual oil measurements. As the project planning and design, there are many different items and pre-deployment requirements for the use of partitioning tracers for interwell projects as well as single well tests. Due to time constraints, we will stick to the basics and case study review. Partitioning studies work by using two tracers with different characteristics. One is a passive tracer that moves with the injected fluid only. In this case, presented in the blue curve, and is a passive tracer. not interacting with the hydrocarbons. The second is a tracer with known K factors or partitioning coefficient. In this case, presented in the red trace. When deployed simultaneously, the arrival of the passive tracer will be first, followed by the partitioning tracer. The delay of the partitioning tracer's arrival is due to its interaction with the oil and can be used to calculate residual and remaining oil in place. This calculation is provided below. Three wells of the pilot study were used to calculate the measurements of oil saturation pre-application of the ASP flood. The blue trace on the left are the passive tracer responses at each producer. During injection, one passive tracer was injected and two partitioning tracers were deployed at the same time. The partitioning tracers are represented by the red and green traces. Utilizing customized software, the timing intervals were used on the right plots for each partitioning tracer. Their specific partitioning coefficient used indicated in the beta part of the table, and oil saturations calculated based on arrival times. The range in saturations calculated were 36 to 37%. After the use of the ASP flood, the residual oil saturation was calculated by repeating the same application of passive and partitioning tracers. Tracers showed the reduction in oil saturation from 36% to that of approximately 2% within the waterflood contacted pore volume. This incremental oil desaturation by ASP determined through the tracer study is in line with the results obtained from an NMR saturation study in the observation wells involved with the project. I would like to provide the SPE number and thank those involved with the case study. The following case studies will investigate the use of tracers to help finding the best rock, landing targets, and increase efficiency of pad developments. We will cover a few key topic planning items, and data critical information. Just as a reminder, the tracer deployment and timing across the stimulation can affect results. Liquid, water, oil, and gas tracers will provide quantitative production and can be designed to provide phase-specific data for desired objectives. Particulate tracers will only provide qualitative data due to the number of multiple complicating factors that cannot be resolved. During the project design, take into consideration the phases that need to be understood to meet the objectives. Often one phase of production will not provide enough data to complete the goals. What masses of tracers should be applied to provide the needed data over the project lifespan given volumes of phases expected to be produced, such as the formation water. Finally, how can I integrate the results with other data sets to include multivariables that may be presented along the wellbore or other additional data sets available? Looking at concentrations of tracer alone and not including the volumes being produced can lead to incorrect conclusions. This is presented in the top bar chart and graphs. Use the mass of the tracer produced so that not only the injected well's performance is properly calculated, but also the volumes of communication can be calculated over time. To dig a little deeper, we include the gamma ray log and define some sections of the wellbore in this case study. We begin with a look at the well's cumulative oil production along the wellbore. This has insight to the cumulative production per stage and may inspire some further investigation and can provide some future opportunities. We include the gamma ray log and define some sections of the wellbore. In this case, 4 defined locations were identified. Below the well log, different colors were used to identify the different completions used during the stimulation to deal with the geology. The key to the upper right identifies the completions used. Slick water, gels, and crosslinks used or combinations along the lateral. During the drilling operations, several logs were run, and these can be included to look at correlating factors or identify principal components linked to production. The red trace represents the total hydrocarbons present in the mud log. Starting from the heel, some obvious erratic changes are present from stages 40 to 28, as well as 2 distinct step changes are observed from stages 27 to 11, and another step change from stages 10 to 1. Below the wellbore, we have now included some mechanical logs. There are distinct changes in the logs following the feature located at stage 31. This also coincides with different production volumes observed by the stage and higher production from the stage on either side. Due to logging issues, the toe could not be logged. The last bit of information available for this well was the completion stimulation data. Completions design and fluid systems can have a significant impact on the production as well as how the well cleans up over time. We have included the average breakdown pressures, the ISIP, treating pressures, and volumes placed using the different traced lines. There is a significant step change in the completions pressures measured during the completions of stages 1 through 10. Often, when looking at cleanup efficiency and production, further insight comes from the production over time rather than the cumulative production. I hope the animation will work for everybody and you will not experience too much lag. The solid bars present the change in production over time, and the translucent grid provides cumulative production over the entire project. Using this, we can see how a stage performed in 2 ways, the cumulative as well as over time. This also removes some bias in the cumulative data due to the stage's location, differences in cleanup over time, and other items that may affect early production. This is particularly handy when evaluating choke changes and artificial lift changes. We're going to take a look at infield development relating to parent-child relationship, tank-style completions, and communication between wells. These can be complicated to evaluate and make determinations from data being provided difficult. There are some steps that can be taken to help. To evaluate the communication, often multiple phases need to be traced. The desired hydrocarbon phase and the completion fluids. Both the established frac length created and determining the effective communication over time. These data sets can provide a lot of insight into the best completions designs, frac order, mitigations for parent wells, and spacing of pad development. The quantification of phase production is critical to understanding multiple variables and the relationship between well to well. The slide presents 3 separate ways to look at data and need to be considered when evaluating best practices. The video shows how water communication can change over time, and the percentage recovered relative to the injection well is in the purple plot above. While the gun barrel view shows another look at how the fracture communication outwards and is downwards. The case study being presented was completed, case study 4 will include parent-child interactions, multiple well pad development, and landing target sections. For each diagnostic investigation, wells were chosen that would provide the best opportunity to provide the most representative data sets. The case study being presented was completed in the Anadarko Basin and had several goals and objectives. As part of the aggregate of the Mississippian, the Merrimack and the Woodford have changing thicknesses across the Oklahoma region, and the well spacing and infill development become more of a 3-dimensional problem with multiple horizons. One goal was to identify the production differences in 2 slightly different landing targets. Stages were traced in the 2 different targets, resulting in clear differences of higher production from the experimental zone than that of the in-zone stages. Those results are provided in the blue bar chart to the top right. The second and third goals were concerning infield development practices, looking closer at well spacing, completions designs, and protecting parent wells. As a baseline test, 2 pads were drilled in a similar stacked configuration. Well spacing of pad A had child wells approximately 1,750 feet apart, and the nearest well to the parent landed 360 feet below the parent, as well as 1,750 feet of distance horizontally. As a mitigation measure, the parent well was shut in and allowed to naturally build pressure from the formation. The results indicated the furthest child well communicated approximately 5% with the tracer applied to well 1A, to the infill well 2A. This suggests there was enough well spacing between the child wells. However, significant communication was observed from the child well 1A to the parent well above. Over 17% of the water tracer applied from child well 1A was recovered from the parent well, demonstrating this well spacing to be insufficient. In the second variation of the pad well spacing remained similar. However, the child wells were drilled in opposite directions of the parent well. In addition, the mitigation strategy was changed. The parent well was preloaded with 30,000 barrels of fluid. As a result, the child-to-child well communication remained similar, but the parent-child communication was reduced by 51%. By using liquid molecular chemical tracers, an operator in the scoop stack play was able to rapidly quantify the effects of different fracture communication mitigation strategies with minimal cost, low risk, and without the need for a large data set or multiple trial and error efforts. The drilling and completion strategy was rapidly adapted with immediate improvements in estimated ultimate recovery, EOR, and net profitability, repaying the investment in the next incremental pad. The results of this tracer study justified additional tracer investigations into the effects of existing fault communication, alternate completions designs, and studies in other producing layers. With that, I will hand the presentation back over to Sadipcha for the question and answer section, as well as closing statements.
Thank you, Patrick. Those case studies were excellent. You certainly covered a wide gamut of topics. I'll be moderating our Q&A now. For our listeners, please submit your questions into the Q&A chat box on your screen. We will work to answer the most common or frequent questions that have popped up amongst today's audience. But if your question isn't able to be addressed in the time we have remaining, don't fret. The team from Tracerco has committed to answering all the questions missed by email over the next few days. So please don't be hesitant in any way in asking whatever question comes to mind. If you're looking for more information about tracers in general, please note that Mr. Hayes has shared both his contact details and a website where you can learn more about oilfield tracers in general, and follow up if you have specific project requirements from either Patrick or Tracerco. With that, let's see what sort of questions are being asked. Okay, we'll start with, can tracers help in knowing crossflow between the layers?
I can take that one, Sudipti, if you like. It's Paul Hewitt here. Thanks for attending this this webinar, everybody. Surendra, I presume that you're talking about water flooding or injection gas tracing there, as opposed to frac tracing. Clearly, in the case of frac pads, we've demonstrated that in the case studies that you can actually measure the degree of crossflow between wells. But in terms of specific layers within a water flood or an injection gas project, yes, indeed, we can do that as well. We have a wide range of unique chemical traces that can be applied, so we can fingerprint not only individual injection wells, but if we are able to isolate injection layers, then we can actually introduce a unique fingerprint into that layer and then measure for its presence in other producing wells, possibly in other layers, and determine whether crossflow is occurring and give some indication of the quantity of crossflow that's going on between those layers. Hopefully that's answered your question.
Our next question is, are your liquid tracers sensitive to temperature?
Do you want me to take that one as well, Sudipti?
Sure, if you'd like to.
Yeah, absolutely. Yeah, thanks, Mathav. Yeah, I mean, this is a great question. I mean, all chemicals will be subject to limitation when it comes to temperature, and we've actually got a significant pressure volume temperature laboratory located within Tracerco, and we tend to test out all of our tracers both before projects, but also in general before they're actually introduced into the marketplace. And we have comprehensive studies showing temperature stability for our full range of oil, gas, and water-based tracers. The most extreme tests we've carried out were for high pressure, high temperature projects around the world, which involved a 12-month test at 190 Celsius. So it was very hot, and we were able to actually determine failure rates for a number of the tracers, but also determine which tracers survived for 12 months at those temperatures. So we have comprehensive data ranging anywhere from 40 Celsius all the way up to 190 Celsius that allows us to select the appropriate tracers for a given project.
Thank you for that. I'm actually going to answer this next one, which is, can stimulated reservoir volume or fracture length be evaluated using tracers? And the answer is, as it so often is in the oil field, it depends. It depends on the circumstances. To a certain extent, the answer is yes. And tracers are used pretty widely to evaluate whether or not the stimulated reservoir volume of a well is overlapping with the stimulated reservoir volume of a nearby well in the same pad or layer, things like that, where you'll actually look towards that interwell communication of tracers from one that is being stimulated to an offset well to determine if you have frac hits or overlapping stimulated reservoir volumes. And there have actually been a lot of interesting studies showing how your stimulated reservoir volume, while they may overlap within a pad or within a layer initially, will with time decrease some and no longer allow those sort of interwell communications. It has been used pretty extensively as well in conjunction with microseismic. So microseismic is an excellent tool to try and evaluate your stimulated reservoir volume, but what it does indicate is where you're seeing rock breaking, not necessarily whether or not the areas where you have created your fracture network are actually in any way communicating with your main prop fractures. So you oftentimes will see tracers being used in conjunction with microseismic, because where microseismic says, here we have broken rock, your tracers to a certain extent can tell you where flow is actually occurring. And by essentially overlapping the two maps, you get a very solid idea of where those fractures are because rock has broken, and where you actually have flow through those fractures that's communicating with your wellbore. As for evaluating true fracture length, that I'm more inclined to say no, tracers are not appropriate for. They'll help give you sort of a ballpark estimate depending on sort of the time and travel distance, but you won't be able to provide a strong numerical answer saying, oh, my fracture half length is 550 feet because of a tracer study. The next question, what data do you have to support applications of this technology in the Permian? Patrick, do you want to talk about some of your experience running projects in the Permian?
Sure. I do need you to repeat the question. I had some communication breakdown there when you started speaking initially. So do you mind repeating the question first?
Sure. The question is, what data do you have to support applications of this technology in the Permian?
Oh, fantastic. No, that's great. We've worked for numerous operators in the Permian who have applied the technology in different layers and formations, from the Sprayberry wolf camps to their own definitions, and found numerous findings that have provided significant impacts on either costs of stimulations and reduce those costs to enhancing the performance of wells and changing their well spacing designs, as well as completion strategies in general, and also understanding some of the better drilling locations. So my answer to that is we've, as you know, as projects are done across the world, percentage wise, the amount of projects being conducted in the Permian is kind of similar, and we've worked for numerous operators, from identifying elastic layers that were restricting the fracs and frac height growth, to evaluating frac order to maximize the outward growth rather than the upward growth, looking at stress shadowing and other mitigations that can be done to constrain the frac or keep the frac in its intended location, as well as identifying some better landing targets. So there's just a large amount of data sets and a large amount of projects that we've conducted in the Permian Basin that have had some pretty impactful results. So hope that answers the question there, Sudipcha.
Well, if not, I'm sure we'll see some follow-up questions. This next question is an interesting one, and I suspect it might get some different answers from everyone in the panel. The question is, where do you see the biggest margin for error in assessing tracer-derived flow quantifications? I'm going to try and answer that first, and then we'll hear from Paul and Patrick if he wants to chime in. So, in my own personal opinion, a lot of the big margins for error are actually avoidable ones. So a lot of the things that can skew your analysis of these sort of flow quantifications, come from bad pre-planning. So when tracers are used that, for example, aren't thermally stable, and you start seeing degradation in the reservoir itself, that can obviously throw off your quantification efforts. And so a good vendor ought to do a fair amount of pre-evaluation to show, hey, my chosen tracers are in fact thermally stable and are for an extended period of time and can provide that sort of data to you. In the case of some of the polymer encapsulated tracers, it's in not having a constant elution rate and not knowing what that elution rate is going to be. Again, this is something that can be determined in laboratory testing long before any project. So there should be supporting data to say, okay, I am at a known rate throughout the life of my polymer tracer inserts. Using tracers that are masked by naturally occurring chemicals within the reservoir, or commonly used well additives, things that might be in a, for example, a chemical pickle that might degrade your tracers, or other compounds that are preventing asphaltene deposition or things like that that might mask the chemical signals of your tracers. These are all things that if you're dealing with an established vendor, they should have a fair amount of data to provide you saying, look, here's the evidence that it's thermally stable. Here's the evidence that it's chemically stable. Here's the evidence that our particulate infused tracers or our polymer tracers are going to be a eluting tracer at a known rate. These are all things that are kind of easy mistakes to avoid if you have done the important work ahead of time. Beyond that, the biggest sources of margin, the biggest sources of error introduction, I would say, comes from your sampling rate. In a frac job, for example, if I'm going to trace a hydraulic fractured well, I know that a lot of my changes are going to happen very early in the life of flowback. And so I want to see fairly rapid, fairly large amounts of samples being derived to try and capture those changes in time. As the well really kind of comes to a steady state, I can start slowing down my sampling rate. But if I know that certain things are going to potentially affect my production behavior, things like choke changes, like bringing on nearby offset wells, I'm going to want to increase my sampling rate to try and capture those changes rather than averaging that out over time. These are all things that really kind of skew your quantification or mask some of the behavior that you're trying to quantify that are big contributions to the error. Paul, did you want to approach this from a different angle? Are there other things that you would see?
I was absolutely going to answer around the frequency of sampling and the fact that, unfortunately, at the minute, we don't have a continuous measurement capability. Clearly, we're working on that sort of thing, but because you have definitive points in time where you're taking samples, then it does introduce a degree of error, which is probably the biggest. So important to make sure that we take plenty of samples and we kind of can gather all of that really important information as changes are made to wells, etc. But of course, that's got to be balanced by the economics of a project.
Since we have already hit 10 o'clock, I think we're going to take just one more question. If you have more, again, please feel free to submit them. We'll either email out a document with answers or provide a website with published answers, or reach out to you individually to answer anything that doesn't get answered today. But our last question will be, how can the longevity of tracers used for fluid tracking be increased? So a fair amount of work with the big vendors has been done to ensure that your suite of chemical tracers aren't going to degrade thermally. They're not going to be consumed by bacteria, things like that. So really, what you're left with is, if you want to increase the length of time that a tracer study can be run, you basically have to increase either the sensitivity of your analysis techniques, being able to analyze smaller and smaller amounts of tracer as it becomes diluted, or increase the amount of tracer that you're actually using. So microencapsulated tracers are a really interesting venue for this, where you are basically taking technology that's been used heavily in pharmaceuticals and cosmetics and trying to apply it to the oil field. So in cosmetics, microencapsulation has been used a lot in things like lipsticks, where the idea is that by microencapsulating the sort of the pigment in lipsticks and allowing it to slowly release over time, you can have lipstick that remains very vivid and bright for an extended lifetime. That same sort of concept's now being applied to the polymer encapsulated tracers, where by using microencapsulation, you can make it so that rather than all of your tracer being available and sort of quickly being dissipated and produced, by having these microencapsulated tracers be exposed to the reservoir at different intervals of time, it's like you are constantly replacing your polymer infused tracer rods with new ones every day, every week, every month. And by doing that, you extend the longevity of your tracer study by basically refreshing the tracer available to be analyzed. Beyond that, a lot of work's being done in trying to improve sensitivity. Work done by Tracerco, for example, with water tracers has just over the past, 5 years, taken the sensitivity of water tracers from parts per billion to parts per trillion. And similar efforts are being done with oil tracers and with gas tracers. So every day, new technologies are coming up to try and make sensitivity higher and to sort of increase the amount of time that tracers introduced to the reservoir are available to be analyzed. Anyone want to add to that answer, or do you feel like that's comprehensive enough?
No, that's comprehensive. It's adapted to me.
Excellent. All right. For everyone who's dialed in today, thank you very much. We appreciate both your questions and your attention. Patrick, do you have any closing remarks?
No, if anyone needs more information, my email address there is on the screen. We will be following up with some of the other questions that weren't able to be answered. And yeah, I look forward to speaking with individuals on project needs. So thank you.
Again, thank you to everyone who participated. Thank you, Patrick, for sharing your knowledge. And thank you, Paul, for your answers during the Q&A session. With that, we'll be ending today's webinar.